Hey folks. All right, so this is the fourth episode in this series on building a scheme-like programming language. So let's just recap what we've done so far. We have a bunch of whole programs that we're able to run now, doing subtraction. So this minus dot scheme, when our interpreter runs this, it produces 1. And if we build, we should see that. Yep. Okay, so we can see that we're able to run some of these full programs. We go back into the main program, we'll be able to see some of the major components. So first we take a program as input, then we convert the input program into an array of tokens, and then we keep calling parse on all those tokens, and we keep calling parse until we get to the very last token. And the reason that we need to keep calling parse repeatedly is for cases like this, where we have multiple separate expressions. They all need to get parsed, and we need to be able to run this program one expression after another. Okay, so that was parsing, then that happens right here. And finally, in the last episode, we implemented AST walking interpretation. So AST walking is just a way of recursively evaluating an AST. So in this episode, this is going to be my last for a couple of weeks on this series because I'm going to Cape Town for a conference that Tiger Beetle is organizing. So in this last episode, I was thinking of just doing some cleanup and some final functions that we did not implement in the last episode. So what I mean there is that inside this AST walking interpreter, we had to provide a bunch of built-ins like if, plus, minus, I think. Func, yeah. I noticed up here that we call it def, but actually the real one that we used is func. So let's modify that. I think it was just in one example. Okay, it was just in one example. All right, so in the last episode, we implemented some of these basic functions that have to be built in, but we only implemented 5, I think, and that's not incredibly useful as a language. So there's some other stuff we could do there, like introduce the ability to have arrays and then have built-in for looping over the arrays. Or another thing that I wanted to cover in this episode was error handling and giving a nice error, because when we first started doing when we implemented our parser, I think we had a lot of panics all over the place. But there's at least one panic there. Were there any in the lexer? Yeah, so there's at least one panic here, one panic in the lexer, one panic in the parser, one panic in the lexer. So maybe let's start there. Let's try out some bad programs. Let's start with a bad lex. How can something even be a bad lex? That's an interesting question. So this panics if we either didn't see a syntax token, or we didn't see an integer token, or we didn't see an identifier token. I'm not actually sure that this can actually ever happen. All right, so let's skip bad lexing. Let's write an example of bad parsing. So a bad parse, this is an easy bad parse, I think, because it will get to the end of the file without ever having closing parentheses. Or even simpler, just this. Let's give that a file a nicer name. All right, and if we run the interpreter on this, I think it's just going to panic, which, like I said, is not going to be that useful. All right, it panicked. So let's make this error better, because what we want to see is if we ran that program, we'd want it to say that it expected a closing parentheses, and we expected it at column 2 if we're starting from 1, column 1 if we're starting from 0. So let's work on that. Now, actually, the interesting thing is that this didn't even fail in the parser. This failed in the AST walker. So even before we can get into improving parser errors, there wasn't a parser error. So I think that we need to do some parser validation. And there's one place that I have in mind. When we have this loop of we need to keep parsing until we get to the end of all tokens, one thing that we didn't do here is make sure that the place where we ended up is actually equal to the number of tokens we had. So here, just I know I said we want to get out of panics, but let's still just panic for a second. If parse index is less than the number of tokens, then it was an incomplete parse. Okay, so that wasn't even this case, but I am curious what this parse index was and what the length of tokens are, because we could still be off by 1. 1 and 1. That's interesting. So maybe it's not a problem of that. Maybe it's a problem of maybe it's a problem of. All right, let's just recap what's going on. We've got this example of missing closing parentheses, and there's no parser error. There's an interpreting error, and the interpreting error happens after parsing. So somewhere our parser is being too loose. It's not being strict enough. So here's the case where it should have happened. It should have got, or okay, if there was a closing parentheses, it would go through this case. When you see a starting case, when you see a starting parentheses, it goes recursively unless it's at the very outer, unless it's the outermost opening parentheses, the first one that you see. So maybe that's the case, because at the end of this for loop, we don't have any check here about seeing a closing parentheses. So maybe let's see where we are at here. And what do I want to print? Tokens. So what I'm thinking is that maybe we need to have a check here. That is, if tokens index 1 dot value not equal to this, then we could panic here. But let's also just print this because I don't know if that thinking is right. Okay, yeah, it looks like that was right. And let's just try this out on a good example too to make sure that we didn't break a good example. All right, so the good example still worked correctly. That's great. So it looks like this was the right logic that we needed to have in here. Let's make this a little bit stricter. Tokens kind syntax token and all right, yeah, just to make that check about this a little bit stricter. Okay. So let's get rid of that format. Let's get rid of this print line. And let's fill this again. Okay. Don't need that anymore. Fill this again. And okay. All right. So now that we have this panic, we can work on improving this error message here. So instead of just panicking, we want to have something like expected closing paren. Basically something like this. And here we could exit, or we could return an error. Yeah, let's just exit. Is it os.exit or is it sys.exit? Okay, it looks like it is os exit, but we do need to port os. Okay. So now we're introducing, or like we're saying that we want this debug helper. So the idea would be that on top of the tokens, we'll add a new debug function. It'll take a message to be descriptive about it, but then this debug function itself should just print out information about where the token was. So we wanted to say what the file name was. We would like it to say the line of code where it happened, and we'd like it to have one of those caret things that said this was where it happened. It would be really nice. And that would be a huge improvement on this panic right here, because the panic doesn't tell us where we expected it. And it's not such a big deal in this simple example. But if this one was valid, like if it was something like this, I don't know. We just, when you have larger programs, you want to know exactly where something went wrong. But let's get rid of these now because we're just doing a really simple version of this. And let's add this debug function on the token. And the debug function doesn't have to be on the token. I just have I don't know. I normally put it on the token. So the token is defined in lex.go. Oh, I already even, okay. I guess in the first episode we must have sketched this out. Okay, so when we sketched this out before, we thought that we'd take the source. Okay, that makes sense because we didn't store the source on the token. But the file name would also be nice to have, and I don't want to have to pass this in all the time. Well, either way, it's annoying because we're constantly going to be constructing tokens, and we're also going to be potentially calling debug all over the place. So it's kind of a wash which place is more convenient to put these. Since we'd like, I can imagine that this debug is going to be useful inside the execution code as well. So maybe at that point you're really far removed from the actual source code. So I think that suggests that we should put it in here. Source and source file. And then this will just become description. So this is what the user passes in along with the error information. So now that we added these two fields to this token struct, we're going to need to fill that in every place that we create a token. So I'm just going to do a search for all the places that we create a token. And I'm seeing a way that could make this easier. So what we'll do is wrap all of the lexing inside of a lexing context. And we'll just store that every time that we create a token. So if we want to do that, let's go back and refactor this. So this will contain that source and the source file name. And everywhere that we want to be able to create tokens, we're going to change the signature so that it acts on the lexing context. And since the lexing context has the source, we can get rid of the source in the signature. And let's keep looking for places to fill in the lexing context. We can go full screen for this for a while. Okay. I guess we don't need to make lex be on that. We can create the, well, no, let's make a, let's make some helpers for this. So let's put lexing in charge of opening the file and reading the file. That way it knows what to, like the file's name, because right here, we were skipping the file's name, but in the lexing context struct, we said that the lexing context struct needs to have the file's name. So let's make lex aware of files. And I think currently this reading happens in main. Yeah, right here. So we'll change this. Bring this in here. And lex needs to be on the lexing context. Let's move this to the bottom of the file. And I see that we're missing the OS import, so let's import OS. And now okay, all right, I see some more errors, so let's fix those. All these lexing functions happen on the lexing context. And they no longer now accept source as an argument. Oh, except for this one. Because eat whitespace doesn't create tokens, so it doesn't really need to have the full lexing context in there. Also, source doesn't exist anymore. These are now lc.source. All right, so now I've completely forgotten what we haven't implemented, so let's compile to see what's missing. 169. This is an array of bytes, so can't convert it directly to an array of runes without first creating a string from it. And line 10. What? Oh, in main, okay. Right, we don't need that anymore. Because the source was on the lexing context. Now, why are you complaining? Oh, because I didn't delete that argument. Rebuild. Okay. Let's try that working example. Still works. Just checking that again. Yeah, all this does is subtracts 2 from 3, and we get 1. All right, so after that refactor, everything's good. We've now got this lexing context to work with. And I think tests are probably going to all fail now because we've added some new structs, and, well, they'll fail for different reasons. So let's fix these tests as well. So I'm going to skip calling the new function here because these are not actual files. And let's copy this elsewhere, because this probably needs to be set up everywhere. All right, let's see what fails now. Parse, copy this again. All right, and now after building, it's probably failing because we've added parse lexing context to a ton of, well, not to a ton of structs. It's now inside every token, and since we have code that was doing direct token comparisons, it's missing all of that now. So we'll have to add where. Actually, yeah, what is failing? Oh, okay, just the overall lex tests. Yeah, these are the only ones that expect it to equal an actual token. So let's add the lexing context. Source file name was memory. This is annoying. You know, let's cheat, and when the tests happen, let's just let's compare each token individually. And let's if we set the returned tokens lexing context to be what we expect it to, then we can do this equality one. It's kind of cheating, but that's okay. Token test of tokens I token test of. All right, let's see if that fixes things. Close. Line 130, where's that? Oh, yeah, .lc. Okay, still failing, then that... Oh, is that failing? No, okay, it's just very verbose. Something's getting printed out, but it passed. Okay, that's good. I don't remember what is printing this stuff out, though. Okay, yeah, it must be these. Yeah. All right. So back to what we were doing, we want to implement this debug function. So this is going to grab the entire line from the source code, print it, where the token is at, print the entire line, print a marker to the column of the current where the token is at, and print the description. All right, so the line we need to grab that, and we need to grab the column. And we do this by just iterating over the entire source all over again. Let's make another iterating helper variable for I less than the source. Let's give ourselves the full screen again. So we're iterating over the runes of the source. R equals source at I. And the location on the tokens in here, t dot location, this is going to tell us when we get to the current line. So there's just a couple things that we need to go to have happen. One is that every time we need to be accumulating the current line by always adding the rune that we're looking at from the beginning. But if we get to a new line, then we need to reset that. That way the current line is always up to date. But there's another exception, which is that if we're past the current, no. The thing I'm concerned about is that the token's location tracks the index, which is not a 2D thing. It's just an index into the flat array. So we're going to need to know when we get to the new line after the index. So we'll just have to think of how to look for that. Because once we get to the new line after the index, then we'll have to break out of this loop. Because we no longer need to keep looking through the rest of the source code. Let's see. If I equals t.location in token line. Yeah, let's do this. So here we can say if we get to a new line, if we were in token line, then we can break out of the debug loop. So now once we break, like this comment says, outside of the loop, the token line variable will contain the entire source code line where the token was. And similarly to this, we want to always be incrementing token column. And once we get to a new line, we want to reset the token column. But let's do that again here. So that and token column will be the column number of the token. Okay. Maybe we're done this. That's all I can think of. Now what we can do is print the description, and we can print the line. And for token column greater than or equal to 0, we can print out space. And finally, we can print out that's near here. So the idea is that we print out the descriptive debugging message, we print out the current token, the current line that the token is in, and then we print out spaces until we get to where the column is located, and then we print out this little helper that says it was near here. And this is failing because, failing because format was not imported. Let's try building this. It builds. Let's see what happens. That was a good example. Here's a bad example. Oh no, infinite loop. Let's give ourselves some more space. Okay, well, here's one place. We're not decrementing anything here. Let's see if that was the issue. Nope. There's another infinite loop. Okay, I is not being incremented anywhere. Let's build and try again. Okay. All right, but now I see this. It's the token line was an array of runes, but that gets printed out in, I don't know if this is hex or what it gets printed out as, but it's not getting printed out as a string, so we convert it to a string. And awesome. This is close. Let's jiggle this example a little bit. I think that this is off by some anyway. Let's change. Well, let's see what this is. Oh, okay. So one other thing that I am thinking of is that we keep on incrementing token column even after we get to the location. So let's change this to if I greater than the location, then we stop incrementing. Or rather, the other way around. We only increment the column until we get to the token's location. All right, that's great. Perfect. Now let's edit this again, though, and let's move around. We do this. Nope, that doesn't look right. What's the issue? Let's print out the token column and let's, well, yeah, just that. And we can also get some more information here. I just want to include the source code and line number and column number in here as well. %s at line %d column %d in file %s. So description, I see that we weren't actually counting lines, so let's add that. Number. Token line number, token column, and the lexing context file source name. Right. Nope, stop jumping around. I'll see dot. All right. And we need a new line at the end of here. And that 1 is because I was printing this out, token column. So is that really where it is? So examples, bad, parse, column 1, 0, 1, 2. No, either way, it should be either column 2 or column, wait, 0, 1, 2, or 1, 2, 3. It should either be 2 or 3. Okay. Well, now at least, well, let's just adjust this again just to make sure again. Nope. That's, so that incremented, but why does this look completely different? I don't have tabs in here, I think. So I'm counting 1, 2, 3, 4, 5, 6. All right, so the token column count is wrong somewhere. Oh, okay. Maybe this should be, yeah, maybe it should only increment it. Before, that was just bad logic there. Okay, that makes more sense. 7, and let's reset this back. All right. Yeah, that makes everything look pretty good. Let's get rid of this debugging print here. And why do we have an extra new line? Because the new line is being included before we break. Yeah. We can put this after here so that we don't include the new line before we break. But now there's a new line from before this. Okay. All right. Well, I guess it doesn't really matter, but let's call it white space trim. Trim space, I think. All right. Now we have a useful debug. That's awesome. That took ultimately longer than I thought it was going to take. But hopefully that makes sense. We have to find the line that it was on, grab the entire line, and then print out the entire line, print out the line number, column number, print out some space so that we can line it up. This is not going to work if there are tabs or other special white space or yeah, any other okay. So the last thing then, since that did take a little longer than I was thinking it would, I just want to get that Fibonacci program working before I close out this series the next couple weeks. So let's see. We make a Fibonacci function, examples fib dot scheme. Func fib just takes one if it's less than 2, then we want to return the argument itself. Otherwise, we're going to call it recursively. All right, let's see what happens. I think that we didn't implement the less than operator, so I think that's where it's going to fail. That was not very a useful mechanic there, is it? See the line of code that it happens. 127. Calling a function that is not built in. Okay, so let's make this error handling a little bit nicer. Maybe function k equals expected function got all right. But now that we have that debug function, we don't need to panic anymore. We can call Or actually, do we have tokens here? Yeah, yeah. It's this. This is a token. So we call token with this nice error message. Why are you complaining? Type value. Yeah, it's a pointer to literal. And looks like we need to import OS again. See if it builds. Let's see what happens here. Okay. Expected function got. Now that is kind of weird. Why did it say that it's over here? So this is great. This part's great. Expected function, we got this. So basically, this is not a function. What I'm not really clear on is why this has the column so high up here. Let's take a look. And let's go sell some more space. So there's no tabs in it. That's one thing I wanted to check. 12. Let's count this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that actually is pretty close to what we expected it to be. Let's see this again. Yeah, I don't. Oh, wait, okay. So it's not printing out spaces before the if. If we print this out, there were all these spaces here. So let's take a look at why those are getting dropped. Oh, trim space. Okay. All right. That's the problem. I did this to try to get rid of new lines, but it can't be that dumb. All right. That's fine. We'll just see that there'll be a little bit more new lines. Okay. Yeah. There, they basically line up. Okay. Yeah. So that's helpful. Now we know exactly what failed and where it failed. So let's add that less than implementation. So we can mostly copy these other ones that are arithmetic booleans, arithmetic operators on binary arithmetic operators. And instead of this, yeah, okay, this can only take 2 arguments, unlike these plus and minus. So we can just directly compare stwalk. 2 arg. Turn the first one less than the second one. There's an error there because it's args, not arg. All right. Expected 1 args to fib got 2. Let's fix that because that's just a panic. So here, instead of panicking, we can do interesting. So this one, we no longer have the AST directly anymore because it was evaluated before we got to this point. So if you were watching the last episode, I had an internal argument about whether or not it makes sense to be nice to some places in the code and always evaluate the arguments for user-defined functions. But Here's a good reason not to do that. Let's leave that for now. And let's take a look at this function. Okay, yeah, I just defined Fibonacci wrong. This is what I meant to do. Fib. It's not that fib takes 2 arguments, it's that you call fib on the argument that's passed in, where you subtract 1 and you subtract 2 from it. And yeah, there we go. Looks like it worked. Yeah, awesome. All right, so now we've got enough to run the Fibonacci program. And that's about as far as I think I'm going to take this. Let's just update the README a little bit. And let's run that again. All right. That's pretty awesome. So there was one other, let's just make one other note for ourselves. And here, so we can give a nice error message instead of panicking. To do that, we need the original tokens so we can debug the code. All right. And let's run format on it as well, and let's add, well, we never did that bad lex, so we can get rid of that, but everything else, add them. The README is up to date and everything looks good. Clean up, bug messages, working Fibonacci program. All right, so that's it. We, in the last 4 episodes, in like 4 hours, we built a simple scheme that ultimately was able to do a Fibonacci program that the user entered. We got some nice error handling in there. We only did AST walking interpreting. In the future, if I feel like coming back to the series, we might get into compiling it back to Go, compiling scheme to Go, or we might do compiling to a custom bytecode, or there are any number of things that we can compile to. Or other stuff that we could do aside from modifying the backend is building out a standard library or adding support for calling Go functions from inside of the scheme implementation. But those are just stuff to consider in the future. Thanks so much for watching this, and we'll see you again definitely after 2 weeks. I'm not sure when I'll do the next one. See ya.